All right, thanks for joining. This evening, we're going to be doing the Connect the Dots session. So I'm going to basically highlight at a very high level view how the models that you've covered so far interact and what they have in common. But we won't go all the way back to the beginning because I did a Connect the Dots session before. So I'm just going to continue from the models after that session to show you how everything fits in. So it's not very technical, very high level overview to show you the similarities, what they're trying to achieve, how they go about achieving that, and what are essentially the differences between the models. So let me share my screen and I'll take you through what I'm talking about. Okay, if you can't see my screen, please let me know. I'm just going to assume that you can. All right, so what do we plan to achieve at the end of the session? So what you should be able to do is explain the common mathematical problem underlying major ML models. But when I say mathematical problem, I'm not really going to go into very intricate maths. It's going to be a very general overview, which is nothing very complex. And I'll show it to you with an example. So you want to understand that most ML models are optimization methods. What do we mean by optimization methods? Well, you're just trying to find the best solution based on some objective, right? And you need to specify what that objective is, and then ML model basically will find the solution that optimizes it in an automatic way. And then you describe how different models make different assumptions about data, explain how geometry influences model choice, and I'll explain what geometry means in the next slide. And we'll connect supervised and unsupervised models. And I'm pretty sure a lot of you are familiar with the difference between the two, judging from your answers in your assignment. So you kind of have an idea of what supervised and unsupervised is. Okay, let's move on to the next slide. What do I mean by geometry? Well, geometry is simply just the distribution of your data. So how is it scattered about in the feature space? So if you had your target variable, so let's just look at the left graph, okay? The left plot, you got these blue dots, and you'll see that it kind of resembles a straight line. So you got your feature, your predictor or variable, and your target variables on the vertical axis. And when you plot the data points, right, you'll see that it follows a straight line. So that's what we mean by linear data. Now this is in a two-dimensional space, so it's easy to visualize, but just keep this image in mind. Even if you go to high dimensions, it follows a straight line kind of pattern. And then you get nonlinear data, and that's on the right. Now the data is more like a spiral kind of shape. And this is nonlinear. So some models work well on linear data, but they don't work well on nonlinear data, and vice versa. And that's what we mean by the geometry. Okay, it's basically all it is. It's the distribution of your data in the feature space. All right. Now, what are ML models really trying to do? Now, the right plot that I'm showing you, some of you may be familiar with something called a contour plot, and some of you may not, and it's fine, I'll explain it. Let's imagine you had a mountain, okay? So you had a mountain, and you have a mountain, right? So let me kind of shade with a diagram. I'm going to do some sketching here to kind of give you an overview. All right, so here we have a mountain like this. All right, if I take a slice here of this mountain, and then you look down on that slice, right? If you look down, you'll kind of see something that looks like a circle like that. If I take a slice further down, then the circle, you'll see the same thing, but the circle is going to be bigger because you can see it is bigger than the first view. So it's like that. And you go further down, and you make slices, you're going to get bigger and bigger circles. So as you get further to the top, you're going to have a very small circle like that. You get the idea. That's what a contour plot is. So what I'm showing here is basically you're finding the optimized value, the value that maximizes something or it minimizes something. If I were to reverse the mountain and do a valley like this, it's the same thing. I make cuts, you'll see the same visual that you see here. So when we say optimize, we're trying to find the values for parameters. So sorry, you could just ensure that your mic is muted unless you want to ask something. All right. Okay, so coming back here, you're finding the values for the parameters. So for regression, you'd look for the beta coefficients, your intercept and your slope, that will find the optimal value for your cost function. And that's this value here. And that's what you're seeing in this contour plot. That's all it's telling you. You're optimizing the parameter space. You're finding the best values for parameter 1 and parameter 2 that will either minimize or maximize your function that you're trying to optimize. All right. So that's what we mean by minimize error, maximize separation. Maximize separation, you would have covered SVM or support vectors, and that's what we mean by separation, and we'll get to that. We also use it to compress information, and that is principal components and also non-negative matrix factorizations, or NMF, right? And discover structure, well, that's where your unsupervised learning algorithms come into place, right? There's no labels or target values you're trying to predict. You're just trying to discover some sort of pattern and structure. And the last 2 points are kind of interchangeable, or reconstruct patterns, right? And ML models do this in an automated way, which is why it's so popular now, because we have computational resources that are much more advanced than what we had 20 years ago, which is why ML models, even though the algorithms, a lot of the algorithms have been in place a while ago, a long time ago, a lot of them just didn't get popular and get used as frequently as it does now, because we have computational resources that are much better than in the past. And ML models are able to leverage that. And with the amount of data that we have these days, which is a large amount of data, we're able to get very valuable information from that. Okay. All right, so the universal problem. So exactly what I just showed you, we're trying to optimize something. So this is your picture of a valley here on the right. Now for regression, a lot of you may have been familiar with this, right? You have your data points represented by these blue dots, and you can construct different lines that can fit this data. But which is the best line? Well, the best line is the one that minimizes. If you look at these vertical dashed lines from the dots to the line, if you had to essentially just sum up the square values of these, you want a line that will give you the lowest sum. A different line will give you different dashed lines. And so every time you have a line, you get a single point on this graph on the right, this valley, because for each line, you have a different cost function value. And so all we're trying to do is, what are the best parameters for this line? In other words, the slope and the intercept, beta naught and B1, that will give you this red dot on this valley, on this graph here. Which values for beta naught and beta1 will give you that red dot. And then that's the best value. Okay, you're minimizing the cost function. And in this example, the cost function is the sum of squares, right? The MSE, I believe. All right, so that's an analogy of what we mean by optimizing the cost function, and I use a linear regression model here to highlight that. And so mathematically, you'll sometimes see this notation here, arg min L, right? The L is your loss function. The min just means minimum. And what the arg means, it means what arguments or what parameters for this loss function will give you the minimum value. That's essentially what I just said earlier. What values for beta naught and beta1 gives you the red dot, right? So that's what the mathematics actually tells you. All right. Okay. So continuing with that previous analogy, all right, with your valley or mountain, you get different types of ways to find those optimized beta values. And those are optimization algorithms. So you've heard of gradient descent, right? We discussed that briefly in neural networks. There's also stochastic gradient descent. Momentum, we won't focus too much on it. I think it might be used more in PDAN, but if you want to read up on it, you can. Basically, it's just an extension of gradient descent, right? Then you get random search and you get adaptive methods. Excuse me. And an example is Adam, and you'll experience that when you're working with neural networks and you're actually coding it, right? All these algorithms are, all they do is it's just different ways of getting to this red dot. Okay, it's different ways of finding the best beta naught and beta 1 values that get you to this red dot. That's what all these methods are: gradient descent, stochastic gradient descent, etc. Each of them have pros and cons, but we won't go into that. But all you need to know for now is that these, when we talk about gradient descent and stochastic gradient descent, etc., they're just different ways of optimizing your machine learning model, right? And so in the diagram on the top, each of these lines are these different algorithms, and it shows you that they can lead to actually different solutions. So depending on the optimization algorithm, sometimes they can lead to different solutions. But if it's if you do it extensively, then most likely they will lead you to the same solution. All right. Okay. Types of learning problems. Now this is kind of very familiar to you: supervised and unsupervised. Supervised learning, we're trying to predict labels or target values, right? We know what the outcome is. Now we're just trying to find patterns from the predictors or the variables that can give us or predict the value that we would expect. Unsupervised learning, we don't have a target column. So you're trying to discover hidden structures or patterns, all right? So sorry, when I said supervised learning, I meant you're trying to find a relationship between the variables and the target variable. Whereas in unsupervised, you're trying to find patterns just amongst the variables themselves, no target variable. Examples, okay? So classification, there's decision trees, SVM, neural nets, right? There's, I know I put classification here, but just keep in mind, it's also used for regression. When you have a continuous target variable, the same models can be used for that: trees, SVM, neural nets. These are just some examples. There's more, but it's just to give you an idea. And then clustering, that's unsupervised. The model that you have covered so far is k-means and db-scan. And then you get dimensionality reduction techniques. Now, these also form part of clustering, right? But I put it here separately because they have an added benefit. They can also reduce the number of variables. And that's principal components and NMF, non-negative matrix factorizations. Right, and then we'll go over each of these models now at a very high level to kind of explain how they work, advantages and disadvantages. All right, so let's start with decision trees. So with decision trees, right, you're trying to partition the space, the feature space, based on a flow diagram or hierarchical rules. So for example, you want to discover rule-based, just think of it as like if statements. It's like if your income is greater than 50K and if your age is less than 30, then your credit score is 650, right? So based on these two variables on the top, you're predicting a target variable where your credit score is a certain value, right? So that's what we mean by hierarchical rules. It's just if statements, right? What is being optimized for this model? Generally, you'll have two types of measures that you can select from. You won't choose both. You can choose either Gini, impurity, or entropy. You can actually try both and see which gives you the better solution. And that is a way that's considered best practice. You don't just want to just assume one of them will give you the best solution. You try both. All right. So how it gets these rules, right? These objectives, for instance, Gini impurity guides the model on how to get these rules. And if you use entropy, you might get the same rules or you might get something different. But which one is better? Well, you'll only know when you actually test the model on some data that it hasn't seen before. All right. Now, what are the strengths of decision trees? Well, if you look at the example on the right, it's easy to understand the rules of why it got to its prediction. Because this person's income was above 50,000 and their age was less than 30, they got a credit score above 650. So it's easy to interpret that, okay, based on those rules. It handles non-linear relationships. Now we spoke about, linear and non-linear data earlier on I think it was like slide 3. Decision trees do well on non-linear data. It's a good rule of practice that to know what model handles linear data and what model handles non-linear data. And the reason being is because linear models work better on linear data than non-linear models and vice versa, okay? So, but the thing is, it's very unlikely you know what shape the data is. Like you would have to just try both models. But often when the data is linearly separable, it's better to use a linear model, all right? And if the data is nonlinear, then use a nonlinear model. Okay, the weaknesses of decision trees. Okay, they can be unstable. And what do we mean by unstable? Well, if you have a small change in your training data, so that means when you train this model on some data, right, the model will obtain a certain architecture. What I mean by architecture, I mean the tree would have a certain tree depth. It may have certain parameters like minimum samples per leaf, etc. And it'll work on certain variables. So for instance, it might work on income and age. But if you change the training data slightly, and then the architecture of the model changes significantly, then that's what we mean by unstable. The model is very sensitive to the data you train it with. So that's what we mean by unstable, right? You make a small change in your training data and that makes a significant change in the architecture of your tree. High variance, you're all very familiar with this. I know this because from your assignment answers, right? It's the difference in your loss for your training data compared to your test data, right? When the difference is large, that's what we mean by high variance. And often that high difference would mean overfitting. That means your training score is much higher than your test score. So that's what we mean by overfitting. So these models have a tendency to do that if you don't tune it properly. What I mean by tuning it, I mean by carefully selecting what depth it should have and all the other parameters that this model will use. All right, and that falls under hyperparameter tuning. Okay. So that's it. Those are its weaknesses. So that's decision trees, right? Let's go to random forest, which is an extension of decision trees. Because if you understand decision trees, then that's basically the building block for random forests, right? And as I mentioned earlier, a single tree can be unstable, but to overcome that problem, you can combine many different trees. And when you do that, you can do it using a random forest, okay? It does it via bootstrap sampling, which is basically just sampling with replacement. And I covered that on my video on random forests. If you want to know more about that, and I do encourage you to familiarize yourself with that, watch that video, okay, that session. And besides just sampling the observations randomly and with replacement, it also samples the features. So not every tree gets all the features. They just get a few features and you combine those trees together. So you have many weak trees, but when you combine them together, you get a stronger prediction when you combine the results. The strengths of it, it's robust, it's strong generalization. That means it can reduce the chance of overfitting because you're combining those many weak learners. Some of you may ask, what is a weak learner? A weak learner is a decision tree, but the depth is very low. That means your tree doesn't go down too far down in terms of decisions. It just has a few if statements. If it has like 1 or 2 if statements, that's considered weak. But as you start increasing that depth, then it's no longer considered a weak tree. All right. All right. Now, the other model that combines many trees is boosting. All right. The difference between boosting and random forest is that for random forest, you could have each tree trained on almost on a different computer, and then you just combine them together. I just think of that analogy. Whereas boosting, you couldn't do that. You can't train the trees independently. You have to wait for one tree to finish, and then the next tree that's trained is developed based on the results you got from the tree before it, and so on and so on. So that's what we mean by sequential. Right? Each tree gets better or improves on the performance on the previous tree. Right? So it's a sequential procedure. There's different types of boosting algorithms: AdaBoost, gradient boosting, XGBoost. XGBoost is probably the most popular one that's used. Light GBM is also used. XGBoost can often, if you're not short on computational resources, generally XGBoost is used over Light GBM, right? But it's worth exploring all 4 of them. The key assumption is that weak learners can collectively form a stronger learner. All right. Strengths, they do very well in predictive performance, but they can easily overfit. So be wary of that. That is a common problem with boosting algorithms, right? It easily overfits. And if it didn't mention it here, you should know that it also handles nonlinear data. So as long as the model uses trees in it, then it can handle nonlinear data, right? So random forest and boosting both can handle nonlinear data. Here's a comparison between, let me see if I can make this. No, I'll just zoom in here. This is a comparison of random forest and boosting. So for random forest, let's imagine you had a democratic committee of fully grown experts, right? And each expert, which is a tree, receives a slightly different subset of data, right? So that's your bootstrap sample, and it's trained to completion. Now, because they are independent, so just as that analogy I gave you, each one is trained on a different tree, on a computer, a different computer. That's what I mean by independent. They have diverse viewpoints, and the final answer is simply a majority vote or the average. Now, for boosting, you can imagine a relay team, all right, where each runner learns from the mistakes of the runner before them. The first runner makes a crude guess, the second runner improves on that, etc., etc. And then you combine the results from all these learners or the relay runners, but you take a weighted average of it. So whichever runner, if a runner does better than the previous runners, then that runner gets the most weight, and so on and so on. And so you take a weighted average, and that's your final result. Okay. Just let me know if you have any questions, all right? But feel free to, yeah, ask if you're not sure about anything. So k-means clustering. Now we'll move on to unsupervised learning algorithms. So k-means, this is the one that you have covered. This diagram on the left kind of summarizes it very well. It's a very common diagram used to explain k-means clustering. If you assume all these data points didn't have any color, they were all black, and all k-means clustering tries to do is it tries to assign a color to it in a way, or assign a specific cluster to it. So all these points here in the orange, they were all initially black, and it found these points to be very similar, so it classified them as orange. These points green, and these points blue. And that's what clustering does. Now, I would say that the disadvantage of k-means clustering is that before you run it, you have to actually specify how many clusters you're looking for. What is that k? Now, generally, you don't know that beforehand. You don't know how many clusters should be in the data, and that requires experimentation. All right, so You will generally not get it right in the first try, but there's a systematic way of actually determining which how many clusters you should have. And that is basically this objective function that you see here. Now, all that function is telling you is that if you took all these points in blue and you worked out the variance of it, and when you work out the variance, remember you have to work out the average, the center, and then you work out the distance of each point from that average, all right? And then you square it and you sum it up. That'll give you a certain value. You do the same thing for the points in green and orange. Now, whichever arrangement of points, maybe you had a fourth color here. If you had a fourth color here, then you would have a fourth cluster that you have to work this out for. Now, when you work out the variance of all of these clusters and you add them up, you want that value to be as low as possible. And so the value that gives you the lowest objective function value, for this example, it would be k is equal to 3. It was when you have 3 clusters. If you had 4, that number wouldn't be as small. Number 5 wouldn't be as small. So that's how you determine which is the best k, right? You're trying to minimize this objective function based on how many clusters you have. Geometry, Voron, I don't think I can pronounce, it's a Russian mathematician, Voronoi partitions. It does it basically using Voronoi partitions. If you just Google Voronoi image or diagram, you'll see basically that's what you'll see the image is the same. All the Voronoi partition does, excuse me, is it's a way of dividing space into distinct regions based on the distance to a specific set of points. So what I'm trying to say is you're trying to arrange these points into a certain cluster based on the distance of the center of that cluster. All right, and that's what we mean by that. Okay. One of the assumptions that K-means clustering makes is that it assumes these clusters. So look at these points in orange. It assumes that they're spherical in shape, right? Often that's not necessarily the case. So that can be a shortfall of it, right? But generally it works well, but just keep in mind that is the assumption it makes. DB scan, which is the other unsupervised method you would have come across, that overcomes that problem. Here, the points don't have to be spherical in shape. There's an additional benefit with DB scan compared to K-means. So let's go back to K-means. If you look at this point in the far right, this green point here, this could necessarily be considered an outlier, not necessarily in the green cluster, right? Hypothetically. When you have outliers, you don't necessarily want to force them into a cluster. But with K-means, you end up doing that. With DB scan, you don't do that. If a point is an outlier, then what happens is DB scan just isolates them and keeps them on a cluster on their own. So that's one benefit of it. You also don't have to define the number of clusters beforehand. Like I said, with K-means, you have to specify the number of clusters. You don't generally know what that number is beforehand. DB scan, you don't have to do that, right? It discovers it on its own. So yeah, those points that I mentioned earlier, that you don't have to be spherical, they can be irregular shaped and isolate outliers. And just like the name says, it's based on density, right? So it's the amount of points you have in a certain volume. If you have a lot of points in a particular volume versus a less number of points for that same volume, then the density is higher for the first one, right? So it clusters it based on that, right? Based on a number of points, a large number of points in a small amount of volume. The strengths, noise resistance, that's exactly what I meant by isolating outliers. Weaknesses, it's sensitive to parameter choice. There's 2 parameters that this model uses, right? The one parameter is your neighborhood radius, which you have to specify. And then you have to specify what's the minimum number of points you want to form a dense region, right? You have to specify that beforehand. But there's ways to optimize those values and to figure out what are the best values for that. So depending on those values that you specify, you can get quite a significant a difference in result. So just keep that in mind. That's one of its weaknesses. Okay. PCA, right? This is another method of unsupervised learning, and it's also used to reduce the amount of features that you have. Its objective is to find the direction of maximum variance. All right. Here, there's some linear algebra involved, and you'd have to be familiar with eigenvectors and eigenvalues. They're just basically ways to decompose a excuse me, a matrix, right? So vectors will tell you the direction, right? That gives you the maximum variance, and the eigenvalues tells you what that amount of variance is. That's what they essentially do. You can combine, so if you had, for instance, let's say you had 4 variables initially, right? You had age, you had income, you had debt, and the last variable was, let's say, debt to income, right? Debt relative to income. Principal components basically combine those 4 variables into some linear sum, like a straight line sum. And each coefficient of those variables will indicate a direction in which that variable contributes to the variance. Right? So basically, a principal component is just a sum of your original variables, right? And all of that summation and that coefficients for that equation are determined in the background. So it's useful for compression, reducing your feature space, noise reduction, and feature engineering. So it can give you, when you say feature engineering, it's basically restructuring new features based on your original features. And that's what we mean by that. All right. So that's PCA. Now, NMF. So NMF, non-negative matrix factorization, just think of it this way, right? If you had an image of a face, you could break that image down into Lego blocks, right? And think of each of those Lego blocks as a feature. Then what happens is you can use those Lego blocks, you can keep adding them to reconstruct that face. And the handy thing about that is because you get to discover what features make up the image. So think of each feature as a nose, eye, ear, etc. They're very useful for topic modeling. So for instance, let's say you have a whole bunch of documents, right? When I say documents, think of you capturing a lot of data on tweets, right? Twitter. You captured a lot of tweets or different users, but they were all discussing kind of similar topics, but you don't know what that topic is. Now, NMF could be used on that data to find what the topics are. Maybe they were talking about a great new a car that's being launched, right? So NMF would it'll discover what the topic is for all those tweets. And when I'm showing you this maths on the right, what that W and the H is. So think of the W as telling you what the topics are, and then the H is all the keywords that were predictive in determining that topic. Maybe it was words like fuel efficiency, speed, luxury, interior. You get what I'm saying. Those kind of words were characteristic in explaining why you got that specific topic. Right? So it decomposes it into those W and H. So like I said with that example with the Lego blocks, because you can only add blocks together to form the face, that's what we mean by the data has to be positive data values. You can't subtract features to get back to the original image. All right. Okay, 2 more models, SVM and neural networks. Okay, now SVM, this diagram kind of summarizes it. What you're trying to do is you're trying to find the best orange dashed line and the green dashed line that can separate your classes. All right. So here, instead of this wouldn't be the best SVM lines. The best lines would actually be going down this way. So because you can see your blue points on the right and your orange points on the left. So you'd want the blue line down there and the orange line down here, and you want as much distance between those lines as possible to separate those classes. So that's what we mean by maximizing the separation margin, right? The points on this line are what is considered the support vectors. And that's the whole objective of support vectors. They're very good for classification, right, when you're trying to separate two classes. Now, SVM leverages off something called kernels. Now, SVM wouldn't be as effective if it didn't have kernels. This is what makes it powerful. You get different types of kernels, polynomial, RBF, sigmoid. By setting those kernels, the model performs better, right? It's able to find a plane that can actually separate the data, because often the data isn't as neatly drawn like how you see here, where you can clearly see how it's separated. Sometimes it's a bit more complex. And when that happens, you have to utilize these kernels to kind of find that separation. Okay. Lastly, it's neural networks. Now, this I covered in the last session. Here, it's basically about layers, neurons, weights, and activations, all right? And there's a forward pass and there's a backward pass. In the forward pass, you're assessing how this neural network makes a prediction and how far is that prediction compared to the actual value. Once you determine that difference between your actual and your predicted value, you communicate that to the model going backwards. And you do this because going backwards updates your parameters, that is your weights and your biases. It updates those values to make the prediction better, and then you do the forward pass again, and then you do the backward pass again. And the key operation to the backward pass to update the parameters is derivatives. Now, that's where derivatives using the chain rule comes into place. All right, so if I had to point you to this update rule here that I'm showing on the right, all this theta is, you can think of it as one of the weights. You want to create the new weight, which is in the next iteration, theta t plus 1. The updated value is what the old value was, theta t, minus the learning rate, which you specify. Right? You can experiment with different values for eta. That's your learning rate. And this whole part on the right, this triangle with this L, all it is, it's the derivative of your loss function with respect to that weight. So this is where your derivatives come in. And I showed you last time how, we did some intensive derivative calculations there. And that's how it feeds into the updating procedure. So derivatives are key to updating those parameters, all right? And they also handle nonlinear data very well. Okay, lastly, comparison. This will summarize it up. Random forests, boosting, k-means, etc. I'll actually just leave it for you to just read through. I'll make this pack available. I encourage you to just read through it and familiarize yourself with these key points and the assumptions that they make. All right. The last one is, I guess, something some of you ask, and you may be wondering, how do you decide which model? So first thing is understand which models are linear and which models are non-linear. And then you won't necessarily know whether your data is linear or not. Unless it's a very small amount of variables, then you can actually just visualize it. If you can visualize it and you can see that the data follows a linear pattern, then use a linear model. Otherwise, use a nonlinear model. But when you can't see it, you just have to try both. Dense or sparse, that's for your clustering algorithms. If the data is dense, and you can see that visually, then you would often use dbScan, all right? Clustered or continuous, that would be for your, you're trying to decide supervised, unsupervised. There's also other components that you want to look at is it a small data set, large data set? Do you have many variables, as in high dimensional data? Some models don't handle high dimensional data very well, so you may want to consider that, right? Some models don't handle small data sets, So you may want to rule them out as well. So familiarize yourself with which models handle small data sets. Which models don't handle small data sets. Then there's the interpretability component. There are some models that are black box models. So for instance, neural networks, they're not easy to interpret. They may do well with the predictions, but you may not understand how it got to that prediction. And that may be important. So if your business problem, if it's important for you to explain to a client why they got rejected, you can't really use a black box model because you need to give feedback to the client to understand why. Maybe a decision tree might be better because you can understand exactly the if statements of why that client got that prediction, right? And then computational restraints. Some models take up a lot more computational power than others. So depending on your computational resources, like if you have availability to high computational resources, then you could, that you don't really have that restriction. But where you do, it is important to understand which models fall in those categories. So you can use these four as a guideline because these are generally the guidelines on how to determine which model. And that's what, if you get involved in data science and data modeling, that's part of your work. There is no one size fits all, one model works for all. You do have to do some experimentation, but guided experimentation based on these guidelines. Okay, that's the end of it. Like I said, it wasn't going to be a technical talk, very high level, and just to kind of give you an idea of how everything fits in. Yeah, that's it for me. Any questions? I hope you're enjoying this. Well, enjoy this course. And then next year you'd get involved with very hands-on coding for these models. So you'd actually get to implement these models on data like you actually would do if you had to go into industry. So you'll get that kind of exposure, which should be, yeah, interesting and exciting. I hope you're looking forward to it. All right, if there's no questions, then we can call it, but feel free to ask away. Michelle, you have your hands up?
Hi, Daryl. I just want to confirm, till when do we have class?
I believe this was the last session. I think
Okay.
this was the last session, yeah. Yeah, so it's revision time for you. All right, thanks everyone, and I really appreciate your time and you joining. Yeah, we shall chat soon. Have a good one.
Thank you.
Thank you. Daryl, sorry, are you still there?
Yeah, I'm still here.